We shall see. So thanks for the introduction. It's my first time here. Appreciate the invite. Happy to talk to you all today about some of our early experiences deploying the TACC Stampede system. Just so you know, I'm one of the PIs of this system. I'm the chief application scientist for the system, and I design most of the system software architecture, installation, and management. So I'm happy to talk to you today. I'd be happy to answer any questions as we go along if you have any, if that's okay, or otherwise we can just cruise through. And before we begin, just some quick acknowledgements, obviously, to our sponsor, which this is a system in the U.S., so it's funded by the National Science Foundation. It's generally available to any academic in the U.S. You can apply for time on it if you're at any institution in the U.S., and it doesn't cost any money, but it's funded by the National Science Foundation. So that's the Stampede Award, and also something that DK mentioned, another award that we have funded by NSF to do some topology-aware collectives and scheduling. So that kind of is who the funding agencies are for this talk. Also, I'd be remiss if I didn't thank all the folks who were involved in getting us through this deployment. So that's a lot of Dell, Intel, and Mellanox folks, and definitely Professor DK Panda and his group at OSU. They're a partner on this deployment, and they've been really helpful in providing a lot of intellectual merit for the InfiniBand side of the deployment. And of course, everybody at TACC who's been working on this for the last, this is about a 2-year endeavor that we've been going on, and we just put the system into production. All right, so an outline for the talk. I will give you an overview of the system in case you're not familiar with it, kind of break it into 2 different parts. One is a base compute part. Another is an innovative component, which in this case happens to be Xeon Phi. I'll talk about the I/O subsystem, and just kind of going to try to sprinkle in some experiences, I guess, along the way. So one of them will be cable management. Then we'll switch gears and talk about software environment briefly, talk about the batch system that we deployed in this case very briefly. And then I'll go through some system speeds and feeds, just the usual kinds of performance metrics that you might be interested for a new system, and try to end with some early experiences, sprinkle in a new feature or two, and show some early people doing early science on the system. All right, so this is Stampede from a high-level overview. This is a picture of one of the rows over on the right. There's 8 rows in this system. This is a Dell-based cluster, so all of the compute hardware and the I/O hardware is from Dell. The processors are Intel, Sandy Bridge in this case. The interconnect is Mellanox-based, so this is running FDR, InfiniBand, as DK said. And it's tries to keep, it's a dual socket configuration in all of the compute nodes. We try to keep 2 gigabytes per core as much as we can, so we did on this system. So that means 32 gigabytes in each compute node. We have 6,400 compute nodes total on this system, full FDR interconnect. We don't have the same kind of island that was discussed this morning, but we do have a little bit of oversubscription on the system. So we have a 5-to-4 oversubscription, just a tiny little bit of oversubscription that we decided to go with to limit the number of core switches that we had. So in terms of the base part of the system, which the base to us is the Sandy Bridge part, we've got about 2.2 petaflops of peak performance and over 100,000 cores. And then there's the sort of innovative component, and this is a coprocessor technology from Intel. If you heard about it last supercomputing, they would have called it Mike. Now marketing has got a hold of it, and they call it Intel Xeon Phi. But this is the mini integrated core processor. Just so you know, the version that we have in TACC is kind of a special release SKU. So our version has 61 cores on the system. All of the mic cards are on site at TACC, but we have had to be installing them by hand, and that's a pretty labor-intensive process. And we've been working on it for a couple of months. We did some before SC, and we're finishing it up now. So we have more than 6,000 installed, so we're on the home stretch. And the way we did this deployment is we broke up the formal acceptance of the system into 2 steps. One was the Sandy Bridge side. That side has already been accepted. We've received payment from the National Science Foundation for that. The second part, which is the innovative component part, is the mic, and we're going to be doing formal acceptance this summer on that part of the system. So we're on track to do that. So if you add up the peak performance of the mic side, it's a little over 7 petaflops. So you add it all up, you're nearing 10 petaflops for this system. And just to kind of give you a feel for the level of concurrency on this system. So obviously, traditional MPI, we have over 100,000 cores for just the Sandy Bridge part. The mics have 61 cores. We have 6,400 of those. But to keep them busy, you can use up to a maximum of 4 threads per core. So if we're looking at about 500,000 physical cores on the system, but if you do the extra threads per core on the mic, then you're approaching about 1.6 million threads on the system for total concurrency. So as I mentioned, we have completed the first phase of the project, which was installing everything, and I'll go into a little more detail on what all that took. And we entered our formal production operations on January 7th of this year. So we've had about 2 months of production on our belt so far. All right, so there are some additional subsystems on Stampede. One thing that we've found out on some of our previous systems is, a lot of people need large, huge number of compute nodes to do their work, but sometimes they need more memory than we can make available on a traditional compute node. So we try to keep 2 gigabytes per core, but they might need more than 32 gigabytes or 64 gigabytes or 128 gigabytes. And so one of the things that we've started doing on our systems is we started thinking about them as sort of a complete computational science platform. So we have lots of compute nodes, but we also have other subsystems. And in this case, we have what we call big memory nodes, where we try to, for the most part, buy as much memory as we can to put in a small number of nodes so that people who don't have an MPI application who can actually fan out across the whole system, who have particular requirements to run a computational biology code, for example, on one node, we can accommodate that. So we have 16 nodes on Stampede. Each have a terabyte memory. They're interconnected onto the same fabric. They share the same file system. So we really do think of them as just a subcomponent of Stampede. In addition to having our large memory nodes, we also have a visualization platform embedded directly into the overall Stampede system. And the reason for this is that people who are doing pre- and post-processing, getting data in and out of a system like Stampede, they often suffer through having to move the data if they want to take it to another visualization system. So we try to move the visualization system to the same compute platform. So on this system, we've dedicated 128 compute nodes on the system, where we've also added NVIDIA Kepler K20 GPUs. And they also have mics in it, so it is kind of a convenient place where people who are interested in looking at sort of the performance characteristics of these new mic architectures can also compare to what they were doing with CUDA on GPUs. So that's one subsystem. And the last bit is, of course, we have the usual bevy of management servers. We have 16 other servers. We have 4 login nodes, 4 data movers, a bunch of management servers that we use to keep track of the system. So that's for doing things like our batch system, running our subnet manager. This is InfiniBand based, so we run a software subnet manager on the system and doing all of our provisioning. We have software that we've sort of maintained and create locally for doing high throughput computing. One of the things about a system like Stampede is that you get usage from people all over the country who have quite a different variety of workloads. So some people want to run across the whole system. They're sort of the Gordon Bell type people. But some people are doing lots of ensembles, and they really might only have serial jobs, or they might have only 16-way or 64-way jobs. But they want to actually submit into the queue and use lots of processors in parallel. So we provide some software to try to aggregate lots of small jobs, put them out onto the system, and treat them as big jobs, so people can get a lot of high throughput on the system. So I mentioned our storage subsystem is provided by Dell storage nodes as well. Our aggregate bandwidth on this system is over 150 gigabytes per second. I'll show you some performance numbers in a bit. And we have about 14 petabytes of capacity. And this is a Lustre file system. It's pretty similar to some of our previous systems. At this scale, all of our file systems are Lustre file systems, so even our home file system is Lustre. And we tend to break up our file systems into 3 different partitions: home, work, and scratch, and I'll tell you a little bit more about that. So to actually deploy Stampede, like many people who were building big systems, we had to actually expand our infrastructure. And so what we did in this particular deployment is we expanded our existing machine room. So if you've ever been to TACC in Austin, Texas, and you visited our Ranger system, which just got decommissioned, it's sitting right here. And this was our new machine room as of 6 years ago. And of course, now it's not enough. And so what we did when we designed that is we designed this wall to be expanded out. And there used to be a parking lot right here. And all these gray things that you see on the picture are new things which were built specifically for Stampede. So this is our new machine room. So Stampede is sitting right here. And this is new electrical infrastructure. There's all of our pumping infrastructure sitting in this building. This is a transformer yard right here. Here's our new chiller station, which was put in. And this big round tank is a thermal storage tank that we put in. And the reason to do that, even, it's pretty common in northern climates, but even in the south where we are, putting cold water in here and getting some free cooling allows us to save a few $100,000 a year. And so it's going to pay for itself over the life of this project, and we went ahead and put it in. So just to let you know, the construction on this really was a pretty fast construction. Normally universities don't move terribly quick. So we actually started this almost immediately after hearing about the award, and it started in November of 2011. All right. This is what the footprint of the machine looks like, and it's just comparing to our other system, which we just took offline, which was kind of roughly comparable in terms of money. So back in 2008, we deployed a system called Ranger, which is about a half petaflop system. It cost $30 million. And when it debuted, it was number 4 on the top 500. It was about 3,000 square feet. Took took about 3 megawatts, and as I said, it was about, I think, 568 teraflops total. And in contrast, this is what we're looking at with Stampede. This is the wall that I mentioned got torn down. So all of this part on the right is new. And it has a very big footprint. And part of the reason it has such a big footprint is because we designed it to be able to take 2 of these large Xeon PHYs, or it could take 2 large GPUs. And that kind of increases the footprint of the system pretty dramatically. So we went from 80 racks over here to about 160 compute racks on the right-hand side. It is about 10 petaflops peak, as I said. And we had to add new power. So we delivered about a new 6.5 megawatts of power into this facility. And this just went offline, and as this has been online for about 2 months. Can't talk about a new system if we don't show some construction pictures. So here's the obligatory construction pictures. It really was very fast. So I mentioned we started in November of 2011, right about the time of SC in 2011. And in February, we were pouring concrete for, this is where the new machine room would be. In March, we had a shell. In May, we were starting to move in compute racks. We couldn't actually do anything with them, but we needed a housing place to keep them, and that was the best place to keep them dry. By September, I'll show you on the next slide the actual install process, but in September we can see we have a lot of the compute racks installed. One thing I'll point out is that we're doing the chilling differently than what was mentioned this morning. So this is sort of the more conventional chilled water loop. And what we have, this is a compute rack here. In between this is an in-row cooler. And that's what's absorbing all of the heat of the system. Now, this is before it's done. So we have a hot aisle containment system. So when it's done, there's a roof. This is the cold aisle. Right here is the hot aisle. There'd be a roof on top of that, and there's a door on it now. And these in-row heat exchangers basically take cold air from the floor, run the hot air over the heat exchangers, and exhaust ambient back into the atmosphere. And that's what's carrying about 99% of all the heat load. These are our new chilling towers. This is the inside of our pumping facility. Obviously, we move a lot of water very fast, so a big engineering effort. And all of this was completed in less than a year, which was the fastest we've ever had a construction project go. So you may ask, well, how long does it take to install 6,400 compute nodes? And I'm sure everybody has their own answer. I can tell you how long it took us to do it. This is basically just keeping track of when we actually provisioned each compute node. And remember, there's 6,400 of them. So we started this is the production compute nodes. Obviously, we had a starter system upstream of that where we got to kind of design our software environment. But once the production hardware started rolling in July, we started provisioning right away. Got through the first 2,000 pretty fast by August. Just kept that pace going. Here is the supercomputing conference, and so we did a top 500 sort of a mixed Sandy Bridge mic run at the end of October. And then we were all finished by the end of November here, and we started our early user program in December. That's where we let some of our friendly users on the system, let them kick the tires, have them give feedback for what's good, what's bad. We began our stability testing right before Christmas in the US, and we went into production in January. So, even this, I think, is a relatively quick install because hiding in here, in addition to receiving all the compute nodes, is doing all of the InfiniBand cabling. And it's about 75 miles of cable that we had to wire up. So while we were installing compute nodes, we were also wiring up the system and doing initial hardware testing, replacing hardware that was bad as it came in. But that's the history of the build-out. So I mentioned the Intel Xeon Phi, and one of the things that this solicitation had, and it actually had a requirement, that they wanted you to introduce a major new innovative capability. And part of the reason is that, we've seen some talks even about exascale today, is we know that we're heading in a direction where, programming models are likely to change. The hardware that is being made available to us as HPC consumers is changing and is not really designed for us. It's designed for a different market. So this is sort of intended to be a stepping stone to start getting people thinking about what some of the new architectures are going to look like. And so what we proposed in our bid was to include these Xeon Phi processors. And as it stands right now, every one of our compute nodes has a Intel Xeon Phi installed. But in addition to this, part of this proposal also includes funds to upgrade the machine. So in 2015, we will get 1,600 future generation mics to put in the system. And obviously, that won't fill out the machine. We'll be looking for more funding to try to do that. But we do have an upgrade path to actually try out the next generation architecture, even as part of this process. So if you're not familiar with mic, I'll give you just a quick little heads up of what it's all about. The basic design ideas is, it's kind of similar in thinking to a GPU that it's leveraging existing fabrication technology where it's been shrunk down, but build a big core and build a big die and put many cores on the die. And in this case, Intel is trying to leverage x86 technology. So it's not exactly 100% x86, so it's x86-like, but it tries to adopt a similar programming model. So one of the nice things about mic is that you can actually just compile vanilla C and C++ and Fortran code for the mic if you want. And we'll show you a quick example of how to do that in a second. But it really, what they try to do is strip some of the expensive features. And I point this out because some of these expensive features are some of the things that we've come to know and love and take advantage of in HPC. So in particular, out of order of execution and branch prediction. So some of the things that have been stripped down to get more cores on the die might also be making our programming life a little bit more difficult. The other big thing about these type of architectures is, of course, the wide SIMD units. And on the first generation, they're 512-bit. It uses GDR memory very similar to a GPU. But this is an important concept as well because we're kind of in the HPC world right now. We're really growing in the size of our vector units. We kind of sat stagnant for about 10 years, and now we're seeing doubling every couple of years. And from a programming standpoint and writing application software, which is going to stand the test of time, these wider vector units are proving to be an issue that we have to think about in our development. All right, so programming models. I mentioned that you can actually just use native C, Fortran, and C++ code. And there are multiple sort of shared memory parallel programming models that you might use on the mic with MPI. So if you're Fortran, you're somewhat limited. You have OpenMP, or you can use the MKL library, which is a math library provided by Intel. In C and C++, you can, of course, use OpenMP and pthreads. Some other nice things in C is an open source project called Silk. And in C++, you also have the opportunity to use thread building blocks. So this is sort of the programming models at the threaded level that we've been looking at on mic. And mic supports multiple offload models. So you can offload everything, but it's probably not necessarily what you want to do. It's fun because it's easy to do, and I've taken 1 million lines of Fortran code and compiled it for the mic and run it and verified that it works just to say that I could. But it's probably not the way that people want to use it every day. What they probably want to do is actually use an offload where things which make sense on the Sandy Bridge core are done there. You offload things which have high degrees of parallelism to the mic, and you do MPI from the host itself, negotiating data transfer. Excuse me. But it does support multiple modes. And the other nice thing about it is that it actually has a very familiar Linux environment, something that we're kind of used to on clusters. So it actually runs a variant of Linux. It's very lightweight, so it doesn't take up much memory. Obviously, there's no hard drives on the mic, so everything has to be done in memory. So it runs BusyBox. You can actually log into it if you want to. You can SSH into the mic. You can run top. You can run GDB. You can attach a debugger, and you can just type on it and run your native executable. So from an interactive standpoint, it's a very nice architecture. And here's just a quick dummy example just to show you how it works on our system. And it's not meant to be scientific. This is really the hello world equivalent of mic. And what we have here is a simple C code. And if you're a SLURM user, you'll recognize something that looks like this. This is on our Stampede system. We're submitting an interactive job. We got a shell back on our compute node. And we're looking at the most trivial C code, hello world, but it has some if-defs in here. Protecting ourselves from the mic. So if we're on the host right here, we're on a Sandy Bridge host. And if we compile, ICC is the Intel compiler. If I compile this, I get an executable. I run the executable like I always would, and I get the output that I would expect. But of course, I'm not on a mic, so this macro does nothing, right? All right, now if I repeat that process, the normal way to generate some mic instructions through the Intel compiler is to add a flag called -mmic. I can repeat this, and I'm going to get a new executable. But the -mmic just said, hey, I want you to actually compile the whole code for the mic architecture. Okay, so if I run a.out on my Sandy Bridge, it tells me something nasty. It says, hey, dum-dum, you're trying to run an executable on a platform which it's not designed for. Right? It's not actually for the Sandy Bridge, it's for the mic. So what I can do on our system, we don't share nodes, so anytime you're on our compute node, you own that node, which means you own the mic in that node. So we allow you to SSH into the mic. This is what I'm doing here, SSH mic 0, and I run that same executable, and I get the same output that I had before, but because this if-def is now valid, I also get this extra output. So it's very trivial sort of, hello world. In real cases, we're doing sort of pragma-based offloads where we're running MPI code on the host, and then on a section-by-section basis, we're using pragmas to offload code to the Sandy Bridge. But just gives you a feel for how it works. All right, so let me talk a little bit about the I/O subsystem. I mentioned we're using Dell hardware. We're running Lustre. This is our first 2.x deployment. We have been in production in the past at TACC with Lustre 1.6 and 1.8. This is our first large-scale 2.x deployment. We basically, we have 76 servers total, but what we do is we divvy those up into multiple servers. So our home file system, which is intended to be small on purpose because it's permanent storage for the user, and it's quoted, and we back it up. And we want this to be small because we have to back it up, and we don't want to be backing up terabytes of data every single day. So this is where people normally keep their source code. It's what we intend it for. And it's very small number of servers. We make the quota small because we don't want people to run out of it using 100,000 MPI tasks. Our two workhorse file systems are called Work and Scratch. Work is about 2 petabytes in size. Everybody gets an allocation on Work. It's quoted as well, but we don't back it up. But it's the one place where we won't remove your files. People get on the order of 500 gigabytes in that file system for a quota. You can ask for more, but it starts off at about 500 gigabytes. And then Scratch is our largest file system. It's about 11 petabytes in raw capacity. This is the one where the people who need large data volumes and high I/O speeds run out of. But because it's shared and it's never going to be big enough to satisfy everybody, it's temporary storage. So we do have to remove files for that once it starts to fill up. Just want to tell you a little bit about how we went about deploying the file system. File systems are one of those things that, you might want to just format them and try them out, but you'll save yourself a lot of effort if you spend more time up front really burning in the file system. And so we spent a lot of time on just designing even the RAID layout for this system. So the way the I/O servers work, this is what 2 shelves look like. So there are 5 nodes in this shelf, but the one over on the left-hand side with all the wires going into it is the actual compute server. So that has 2 Sandy Bridge processors in it. So in the Lustre world, this is our OSS, our object storage server. And then The 4 trays on the right are just storage trays. So you can see they pull out vertically. Each one of those holds actually each one holds 16 drives. So we have 4 of them total. So a shelf holds 64 drives. And each one of the drives on this system is a 3 terabyte drive. And these are all SAS drives. So all these cables are done so that we can actually have active passive failover in Lustre. So this compute host here, not only can he see all of the drives, all these 64 drives, he can see all of these 64 drives as well. And that just allows us to maintain our Lustre file system and do failover should one of the OSSs crash. And I'm sure if anybody in here has ever run Lustre, they've experienced multiple OSS crashes. And we are no different. So this is kind of what the raw storage looks like. We use RAID 6, and I'll show you a little bit more about that. I did mention we spent a lot of time on this, and this is kind of lessons learned from our previous deployment where we spent a lot of time on the RAID configuration as well. We get the box, and we spend a few months with it figuring out what we'd like to do. Our final layout, this is just one of the RAID sets. Could care less actually what it looks like, but the thing I wanted to tell you is that we're using RAID 6 in an 8+2 config, and we have 64 drives total that we can play with. So we have 6 OSTs on each OSS, so that takes up 60 drives. Then we use 2 drives in a RAID 1 configuration where we put our Lustre external journals. And so we have 6 journals which we divvy out to 6 OSTs. And so that's 62 drives. And then the last 2 drives we just configure as wandering hot spares. So we do use all 64 drives in this particular configuration. Once we came up with that config, we spent a fair time just burning in each RAID set. Over and over and over. We spent a few weeks actually burning in the drives and flagging anybody who had too many bad write sectors and replacing drives. And kind of when it's all said and done, this plot over on the right gives you a feel for the kind of repeatability that we see on the storage servers once we get them kind of the way we like. So what we're looking at is the write speed to an individual RAID set. And remember, there's 6 RAID sets per OST. And it shows you that we have pretty consistent performance across the board. It's getting about 595 megabytes per second. But that's for one MD, and this is writing in parallel. So if you wanted to think about what is the performance in the box itself, it would be 6 times this. So you're looking at about 3 gigabytes per second. But this is in the box. This is no Lustre. This is just writing to the RAID set. But once we get something like this, we're pretty happy and feel like we're ready to move on and actually build the file system. And once we built the file system, we tested it, of course, and we had to meet some performance projections. And what we did up front is just measure to one single box through Lustre. And we did occasionally actually see peaks of almost 3 gigabytes per second, which corresponds to almost what we expect the raw peak to be inside the box. We then verified scalability. That's one of the nice things about Lustre in our experience is you can expect pretty good scalability into the hundreds of OSSs. And we saw the same here. It was greater than 95% scaling efficiency from 1 server to 58 servers. And then we did our full system I/O test. So the plots over here on the right show you the results. The top one is using a Lustre stripe count of 1. And what we're doing is basically using every single compute node to write a file, in this case a 2 gigabyte file. And we peak out somewhere around 160 gigabytes per second. We repeat the process with a Lustre stripe count of 2. You would expect that now, because we're banging on, every write is now talking to 2 OSTs, we expect performance curve to change a little bit and for our peak to move to the left. And that's exactly what we see here. But still, the thing that we're relatively pleased with is that we're not falling over too far using every client, right? We're still maintaining 140 gigabytes per second with a stripe count of 2. Or 160 with a stripe count of 1 using every single client on the system. So these are our peak read and write speeds for the system. We were really only trying to get about 100 gigabytes per second, so we exceeded that pretty good, and we were pretty happy with the file system. Now I thought I'd spend a little time talking about sort of one of the evil sides of supercomputing. Maybe you don't see it too much. If you've built the system yourself, you've certainly seen it. Just talking about cable management. And as you can imagine, bringing huge numbers of IB cables into a central location can be a bit challenging. And you really want to do a good job because you want to be able to replace your line cards in the field, so you can't have them all completely blocked by every cable. You want to have traceable port mappings. And ideally, it'd be nice if it didn't look horrible. And Stampede is an all IB system. right? So the MPI traffic is IB, the Lustre traffic is IB, MPI, everything is IB. We do have a back-end Ethernet network, but all the high-performance work is done over IB. So we have a lot of cables. So internally to a rack, all of that cabling is copper. We have about 6,400 copper cables, which go from compute nodes to leaf switches. One of the nice things for us on this deployment was we didn't have to do that, so that was a Dell responsibility in this case, and they did a really nice job actually delivering the racks fully assembled. So this is just a picture from their operation line with folks who are working on the racks. You'll notice these are real tall racks. These are 48U racks to accommodate all the servers in there. But they did all the Ethernet and IB wiring local to a host and just delivered the whole thing. What we were responsible for was wiring up these guys. So this is a picture of one of the core switches. This is a Mellanox switch, 648 ports, and we have 8 of those. And so we had to actually wire all of those up. And we had about 5,100 cables, all fiber in this case, and about 75 miles. So one of the things that we kind of learned from is we had some experience on a previous deployment actually with our Ranger system, which had a very nice switch. So if you ever came to TACC, these are the only two places, the only place that I know that has this particular switch. I know there's a smaller one in Europe somewhere, but this was something made by Sun, and it was a huge switch. It could actually handle 3,456 ports. So cable management was a big deal, and it's kind of where we really learned a lot on how to try to think about large-scale cable management. So I think this is one of 2 of them that we had. It looked good. It had these side posts. But the thing in this case, you'll notice the cables are coming up from the bottom. And then they're organized nicely up to the top. So the trick, of course, in this case is that you move the disaster from where you're plugging in the cables, you move the disaster to the floor. And so we kind of realized that relatively quickly, and so we started to create some jigs to help us in this case. So you can't see it, but this was the Cable Thingy 9000. It's a very official name that we used in this deployment. But once it was all said and done, we replaced line cards multiple times. It was very easy to do. The problem is, as we moved to new machines, even smaller machines, it didn't seem like there was the same kind of cable management designs available on the market. So the next machine we built, which is a small little guy called Longhorn, which is only a single 324-port switch, we kind of cheated, and we tried to borrow from the Ranger approach, and we just built something at home. So this is very simple design. It's wood. We use Mellanox cable tray here, mounted on the side, cut a hole in it so the cables can go through it. And you can see once it gets mounted onto the rack, all we do is take the sides off, put this thing on so that we can actually run our cables nicely. In this case, again, from the ground, you'll notice we even borrowed these waterfalls on the bottom where we could route cables up. And when it's all said and done, you still get something that looks relatively decent and that you can swap the line cards out pretty easy. So that was Longhorn. I'll point out we tend to leave all of our, if we have any spare ports, we try to leave them in the middle so that if we do have to replace a cable, we can just add it in the middle as opposed to having to unplug everything. So that's when we started kind of doing some custom work for our cabling. As we moved into bigger systems, like other folks, we started switching to overhead cabling, similar to what we saw this morning. And first time we did this was on our Lone Star system, which is about 2,000 nodes. And this is kind of a picture of what our design looked like. All we do is use commodity ladder racks, commodity racks on the tops of the compute racks. And we have streets which run down the length of the row, and then we have highways to actually get cables between the rows. So pretty standard stuff. And this worked really good, although we needed a new cable management design, which I'll show you in a second. But the only thing I will say is, based on this experience, one thing that we did different on Stampede, and this is a rendering of Stampede, is our highways we actually mounted from the ceiling. And the streets still mount to the top of the racks. And the reason for that is then you never have to get yourself into a situation where you're actually running cables up these rungs. And it made it a little bit easier on us. So one thing we did have to do, though, is design a new cable management strategy. So this is my garage again with a new rack when we were doing Lone Star. And what we did in this case was try to design something where we could organize our cables, which were coming from the top. And you notice we have kind of very coarse vertical vertical paths, if you will, coming from the top. And then they get turned and they run into more fine-grained horizontal trays, and those map directly to where leaf switches are. And then, you know, that's prototype, and then once you pop it on the guy, it looks like that, and it looks real nice. And that worked really good for us for Lone Star, but we had 4 core switches there, and on Ranger, on Stampede, we have 8. You need 1 for both sides, so that means building 16 of these disasters, and I'm kind of slow at doing it, so I really didn't want to. So we came up with the next version, which is the Cable Thingy 9001, very, very official. This one we updated to accommodate fiber because all of our runs are fiber, so there's some little lips on here to try to hold the fiber in. Real simple design, but kind of mimics what we did with wood. But the M in this case is that we wanted to have someone else make it and do it in metal. And this was a nice collaboration with Dell. They had one of their sheet metal contractors. I gave them CAD, and they built this for us. And then we did the same thing, mounted it on the side of our compute racks. You'll notice that we take the sides of our panels off to accommodate this, but overall it looks pretty clean. We do tend to use extra wide racks, and so that when we do mount these on the side, we still have a little bit of space so that we can stand and do the cabling after it's all said and done, because we still kind of adhere to a typical floor layout where we just have one compute rack on a floor tile. So this is what it looks like when it's all done. Long story short, cabling can be a pain if you don't think about it, but this is kind of what it looks like when we are in the process of cabling. These little things are my wife's hair ties, also very, very quality work here. But I think a pretty clean design. Found some little guys to help go around the turn, but we've replaced line cards on this system as well and have had no problems. All right, so we're going to talk a tiny little bit about system management. Obviously, we're running Linux. We're use kind of something in-house for the most part to do all of our system management, something we call LOSF, which is just Linux Operating System Framework. The one thing that we do use externally is something to do our bare metal provisioning. And what we're using these days for that is something released by Fedora. It's called Cobbler. It's real nice. It's Python-based. We haven't had any problems with it. But that's really, we just use that to do our bare metal provisioning. Then we use our system to bring everything up to date. And we manage all of our own distro RPMs and everything that we do internally, like every single package we install, be it an application, be it an MPI stack, say from DK, all of that we build as an RPM, and then that makes it much easier to manage across the system. So this just gives you a feel. Right now, I did a snapshot on the system of the number of packages that we're sort of managing on a typical compute host. So about 175 OS packages. These would be things that you would get from a distro. In our case, we're using a Red Hat type of distro, although it's CentOS. And then all of our packages, all of our third-party things that we build are also RPMs, and it's quite a large number. So these are things like Intel compilers, MPI stacks, PETC, Hyper, all the kinds of packages that you're used to on an HPC system. And we're over 300 now and managing upwards of 100 config files. And we have a very simple system. We do most of our software updates on planned maintenance. We tend to do that on Tuesdays. And we've used this to do multiple upgrades so far. So we've already upgraded even between OS distros, between 6.1, 6.2, and 6.3. So main thing I want to say, for the most part, nothing revolutionary here. Just kind of minor tweaks to stuff we've been doing for a while. But I will say that adding something like Mike does actually introduce a new large software stack, and one that's been evolving quite rapidly. Intel's been releasing new software drops almost monthly. So that has proved to be a little bit of a challenge, and we've been iterating with Intel on how to make that easier. One of the things that has been a little bit of a challenge is doing updates. Sort of Intel, when they started this process, was in the mindset of that, well, people will deploy Mike, and then when we're going to do an update, they'll just remove all the old software and then reinstall all the new software. And obviously, in a production environment like we have, we don't really want to operate that way. We want to be able to move from one snapshot to another. So we've been working with them to make that upgrade process a little bit easier, and it's coming along quite nicely. The other thing you might want to think about, should be aware of if you're going to be deploying any Mike clusters, you need to give a little bit of extra thought to networking. And this is something that we didn't appreciate when we did it right up front. And one of the things that Mike actually has support for is you actually have the capability to do MPI transfers from one mic to another mic. if you want to, right? I mean, so a traditional thing would be to do an offload where you do an MPI on the host and then you're offloading to mics. But if you wanted to, you could run natively on the mic and send MPI traffic between multiple mics. But to do that requires a little more design and thinking on your networking. And so, you know, I just put these first two bullets here to say kind of what we did up front, which would be pretty typical. We have a base Ethernet network. In our case, for certain reasons, for some of the software that we deploy, our compute node IPs are actually real routable IPs. They're public network IPs. So we can't ask for too many of them. We have 6,400 hosts. You know, we can't ask for an infinite number. So we asked for 8,000, which should be more than enough to accommodate the system. We also have IP over IP, which normally we use for anything local. If we need something special, we can revert to a private IP space on our IP over IP. But the way mic works, to actually do job startup, it kind of wants to use the same kind of TCP IP mechanisms that you would use on the front-end host, which means that every mic needs to be able to see every other mic. And you have a bit of a gotcha because the software does not yet work with IP over IP. So you're forced into, right now, actually having a real TCP IP network that you can route between two mics. And we had a problem because we only reserved 8,000 hosts. And so if we really wanted to do that, for all of our mics, we need our 6,400 compute hosts plus our 6,400 mics. And we didn't have enough space. So this is one thing where we kind of had to re-engineer our design. And what we ended up doing was adding another VLAN network to our system. So using our existing Ethernet infrastructure, we defined a new VLAN. Of course, we made it huge. It's private, so it's a Class B. And then what the Intel software provides is a mechanism to actually connect your mic to a Linux bridge on the compute host. And you can put all of that on the same VLAN. It's kind of a lot of nefarious network protocol configuration. But once you get it set up, it works as you would expect. And on our system, all 6,400 mics can see each other on this VLAN network. And that allows us to do MPI between them. One other new thing on this system, in the past we've been an SGE shop primarily. And in this case, you know, with sort of the changes in SGE over the years, we thought we should evaluate something else. And we evaluated SLURM prior to the deployment of Stampede. And we were mostly satisfied with it, so we did actually deploy it on Stampede. I was just going to say a little bit of the experiences from someone who had never used SLURM. Overall, I think it's been quite good. If you're not familiar with SLURM, it came out of Lawrence Livermore originally, and now there's a company around it. It's used in a number of supercomputing centers. But our experience has been pretty good. We are using the multi-factor scheduling plugin, which actually seems to be working great and has solved some of the problems we had with our previous scheduler. And in particular, on our systems, we have such a massive diversity of job sizes that scheduling large jobs while you have small jobs can be a problem. And the SLURM scheduler seems to do a pretty good job at this. So we've been able to run 64,000 processor MPI jobs, you know, now while it's in production without having to do any hand-holding to the scheduler, and it works as you'd expect. The other thing we like about it is it has really an excellent interactive job submission mechanism. So the idea of being, you want to do an interactive job, you just want a bash shell or a T shell on the back end, and then you want to run MPI. They have a very good support for this, and we use it routinely to submit interactive jobs up to 32K, and it, for the most part, just works. So we like that a lot. It's reasonably responsive. We're in production now. We usually have anywhere from 500 to 2,000 jobs in the queue at any one time. Of course, it's managing about 6,000 hosts. Occasionally it gets bogged down, but for the most part, it's reasonably interactive. It's very easy to build, very easy to deploy. One thing I'll talk about in a second is we have had some issues with the topology-based scheduler, so we're still working on this. We also found that it has a job submission filter, but it really wasn't ideal or really up to the task for what we wanted to do, so we created a new one. And we don't use the SLURM PMI linkage. So we manage all of the task layout ourselves on the system just because we're quite familiar with it and how we want to have total control over all the affinity options and kind of control that for our users. So we don't use the PMI linkage. Some wish list things. One thing that we found interestingly missing from SLURM is it doesn't have a load monitor. The idea that you can not schedule jobs to a host that has a load more than one, for example, is missing in SLURM. It's the first batch system I've come across that doesn't have something equivalent to that. And the only other comment we might have is we would like to have a little bit more flexible resource management that's divorced from the SLURM database. So it's kind of, if you want to use all the bells and whistles of SLURM, you kind of have to buy into using their database. And because we're an existing center and we have our own infrastructure, we don't really need all the capabilities of their database. So we're sort of, we'd like to have a little more control without having to use the database all the time. But overall, very good. This is the job submission filter, just to give you a feel for something we created. This is using SLURM's plugin mechanisms, which are quite nice. The API is really nice. You can create things very quickly. So all we did was create a filter that every time a user submits a job, they run through a process of our own control where we can make decisions about whether to accept the job or not. And so the thing about it is it actually it removes all of the authority from SLURM and gives it back to us so that we can control in a simple manner. So, we verify things like you're submitting from a submit host, that you're not submitting too many jobs. It's a classic supercomputing center thing where, for whatever reason, people get mad if they see another user has too many jobs in the queue, even if they're never going to run. For some reason, there's a psychological effect. So we limit the max number of jobs. Another thing we do, which can be sneaky if you don't do it, we make sure that a user's not over quota when they submit the job, because of course, if they're over quota, their job's just going to fail anyway, and 9 times out of 10, they're not really going to understand why. So we check that at job submission time. We have our own independent access control list that we enforce. And we also have this mechanism where, let's say we detected a user who is causing bad things on the system for whatever reason. The usual MO would be they're doing something crazy on the file system. Well, now we can give a custom message to that user saying, hey, we noticed you were doing crazy things on the file system. Please contact support and we'll work with you. So it's a nice way to give some feedback to the users when you don't allow them to submit a job. And I thought I'd show real fast some quick gotchas that we encountered. It wouldn't be a large IB deployment if we didn't encounter cable problems. And this particular deployment was no different. One was very, very simple. This was just a kind of a tight cable radius on some of the copper cables which were delivered in our first few racks. Caught very quickly and rectified at the plant that was doing the assembly. And that was a very simple problem. One that took a little bit more time and we needed obviously some more help from Mellanox is, actually Mellanox came in and told us that they'd identified some potentially bad cables. And the good thing is that they had total traceability. They could tell us exactly which cable was potentially bad, and we could run some monitoring tools with the InfiniBand fabric up, and we could find out which port they were connected to. In the end, we did isolate a batch of bad cables, and our particular deployment had about 550 of these cables. We had installed about 200 of them, so we did have to remove a few hundred cables from the system, and this is what I did with them. Other interesting gotcha that we had was a case where we do a lot of recertification every time we run on the system, and we had a case where when running stream, we noticed that the performance was getting slower and slower, and it only happened after the nodes were up for a long time. You could reboot them and everything would be fine. And once we finally clued into this, it was determined that it was just related to file system caching. We'd seen this kind of behavior before, but not at this level. And so one of the things we did is we changed our SLURM epilogue mechanism to flush the caches between every job. And once that's done, this is the kind of level of repeatability that we see on our Stampede system. So this is just looking at stream at every single compute node on the system. And obviously, it's pretty tight gathering there. Averaging about 75 gigabytes per second. You might ask, what did you have to replace during deployment? These are the kinds of things we had to replace. Our number one thing in the deployment was motherboards, but I should say that that number is probably a little bit artificially high because we realized as we were going along that there were some other things which were field replaceable units, which we could have replaced instead, and in some cases they were kind of using a big hammer and replacing the motherboard as opposed to the part which really need to be replaced. But nothing out of the ordinary. I mean, remember that we have 6,400 of these compute hosts, so not a crazy amount of replacements. And by the way, this is all prior to actually going into production. So now I'll try to go through some speeds and feeds real fast. I think we probably have about 5 minutes. Is that about right? 5 to 7? Seem okay? All right. 10 minutes, all right. So this is a plot similar to what DK showed this morning, just puts into perspective some of where we've come on the InfiniBand side of things. This is just point-to-point measured at the MPI layer. This is using MVAP-Pitch2, and it compares it to some of our previous systems. So Lone Star was QDR. Ranger, which I mentioned just went out of production, was an SDR system. So, we're topping out at over 6 gigabytes per second, which is, of course, the FDR link speed. But the other thing that's nice is that we're getting more usable bandwidth at smaller messages here. So, if you're sending a 1K message, whereas before on a QDR system, maybe you were getting a gigabyte per second, now you're way up here into greater than 4 gigabytes per second. So just the fact that the peak is so much larger, we kind of get more of a usable sweet spot here as well, which is nice. So that's the bandwidth. This is latency. This is also measured at MPI level. So on Stampede, we have a fat tree. So this sort of shows you the minimum latency and the maximum latency. So minimum latency occurs over 1 hop. So this would be going over a leaf switch and a compute rack. And we're approaching 1 microsecond. We get about 1.07 microseconds with MVAP-Pitch2. And then the max over all 5 stages here is more than a factor of 2. So it's not trivial. It's over 2.5 microseconds. So these kinds of differences is some of the motivation for why we continue to think about topology-aware mechanisms, because there's such a drastic difference between this. This is memory bandwidth. I mentioned we were averaging about 75 gigabytes per second. This just shows you kind of how much memory bandwidth you can sustain with varying number of cores. And it's looking at 2 different modes. Over on the left-hand side, with the blue, is where we have compact layout, so we're putting all the threads on 1 socket. On the right-hand side is a interleave layout, so we're interleaving threads on the 2 sockets. And the thing to point out is, of course, that we can saturate the memory bandwidth with fewer than the total number of cores, which is pretty standard for all these commodity processors these days. So with 8 cores, we can get over 70 gigabytes per second. And then as we continue to add more cores, we're basically saturated at that point. This is something which was also discussed briefly this morning, which talking about turbo mode. This is presented a little bit differently, but just to point out the same kind of thing, we're running with turbo mode on Stampede as well. Our nominal speed is 2.7 gigahertz. The peak speed is 3.5 gigahertz. So the point is just that if you were to run LINPACK, for example, on these nodes, I kind of am showing it differently. So I'm basing all of my performance on this nominal value. So if you base it on this value and you run 1 thread or 2 threads or 4 threads, you'll notice that you get more than 100% efficiency. And that's because of turbo mode kicking in. So just pointing out that, which I thought was a very interesting discussion this morning from class, that this is kind of another knob that we have at our disposal to think about. Maybe we should use fewer threads at certain times to actually take advantage of the turbo throttling. This is looking at full system results of just running something like LINPACK. The Sandy Bridge processor, you probably know, can get really high efficiencies on LINPACK, almost Itanium level. So over on the right-hand side, we're looking, these are LINPACK running across the whole system, all 6,400 compute nodes. And all we're looking at is varying the memory footprint. As you know, if you've run LINPACK, you usually get more efficiency with the larger matrix that you run. And so with a very modest 2 gigabytes per node, you get over 80%. And if you go up to 8 gigabytes per node, you're breaking 90% efficiency. And that's across the whole entire system. Now that's running in a homogeneous mode where you're not using the mic. Obviously, we did a case in October, actually, where we used Sandy Bridge and mic. And that's what we submitted for the top 500 list that got Stampede ranked number 7 presently. Just to kind of give you a feel for how the file system performs under normal production, one of the things we do is submit an I/O test job every day. It kind of runs the same kind of thing. A user might run, it goes through the queue, it behaves as a regular user job, and it writes 4 terabytes of data from 512 hosts. And this just shows you the variability over the first month of production. Obviously, I/O is something that is a shared resource in our case. We don't have a quality of service mechanism that can be applied to the I/O subsystem at the moment. So you do see some variability, and we see probably at the lowest here where somebody was likely banging on the file system about 80 gigabytes per second, and then averaging somewhere around 120 gigabytes per second. Again, this is from a relatively small number of hosts. You might be curious to know how much data growth we've seen in the first couple of months. How long does it take to generate a petabyte of data? And in our case, we broke a petabyte right kind of at the beginning of March. So it took about 2 months to actually get a petabyte of data on the scratch file system. So we haven't started purging yet, but it won't be too terribly long. Quickly, some mic results, and these are measurements Intel made, just speeds and feeds. You can probably look most of these up. Main thing, this is single precision GEMM, double precision, stream over on the right. Probably most thing of interest here is Limpack equivalent. On our Sandy Bridge, we get about 330 gigaflops. Our mic, we get over 800. So the point here is that the net effect of these is it's very easy to get a teraflop of performance on a single compute node of Stampede. It's trivial to do. A couple little things I wanted to just point out, thinking about mic. Vectorization is super important on these kinds of mini cores, and this just shows you some impact of vectorization where we're looking at a DNS kernel. This is a kernel that we use in doing direct numerical simulation for fluid mechanics, but one of the things that it does is just call a 2D FFT, and what we're looking at is that FFT done in FFTW, which is an open source library, versus MKL. And if you look over here on the right, this is actually on the development platform of a mic, and you'll see that the orange, sometimes we get a factor of 2 more performance out of the MKL library. And the reason for this is just because the Intel developers have had more time with this thing. And so the particular code that they're generating is getting much more vectorized in this case. But you can see pretty significant performance implications if you don't have vectorized code. Another thing that is huge on mini-core is affinitization. So this just shows running a code natively on a mic and using different types of affinity options where you place the threads. And what we're pointing out here is positive percentage means it runs better than not setting anything. Negative means it runs worse. I think the interesting thing is that it's all over the map as to how these settings can impact your application performance. And it varies by application. So the main point here is that if you get into some mic programming, you owe it to yourself to, once you're kind of ready for production, try all the different affinitization options to see which one provides the best performance. And as we get towards the end here, I just want to point out a new thing that we have available on Stampede. DK talked about this a little bit, which is the fact that topology has a big impact on performance. We saw that with the latency measurements, and it can be different depending on the type of topology. So we have something over like on the left-hand side, which is a fat tree. This is actually Ranger, but Stampede looks very similar. We've been working with folks at San Diego Supercomputing Center who actually do a torus with InfiniBand. And so these are graphical representations of the 2 different networks, which are quite different. And if we can take into account some of knowing about that topology, as DK talked about this morning, we can actually have a pretty significant impact on applications. And so over on the right-hand side is an example of one where we're running on Stampede up to 8,000 processors. The red is not doing anything with topology, and the blue is using the topology-aware mechanism. And we get about a 45% improvement. And one of the things we've made available on Stampede is a mechanism that any user can actually query where they're at in the fabric. And it's host-based, so you can do things like this. You can query 2 different host names, and it'll tell you either the number of hops between those hosts, or if you really want to know the route, it actually caches all the routes. So if you're an InfiniBand person, you'll recognize these as switch GUIDs, and it actually caches all the switch GUIDs and gives those back to you. And that's something that we put into production on Stampede. I'll skip these guys because we only have a couple of minutes. In fact, 1 minute, and just give you a quick couple of things of science highlights. It'd be impossible to do everything on the system. We've had, by the way, 600 active projects so far, 11,000 users in the first 2 months. One group is doing modeling of earthquakes. These are fault lines in California. And these results, the interesting thing about them is they're already going into being fed into the U.S. National Seismic Hazard Map. So results from the system are already going into some production data. That's from Tom Jordan in California. We've also got some of the NAMD folks, Karl Schulz, whose group is responsible for NAMD. They've been on the system. They burned through a huge number of hours. They started doing production almost the day they got access to the system, and they've been quite pleased with it. They're doing molecular dynamics. This is an example from UT Austin. This is Omar Gattas. He might see him occasionally at the Gordon Bell talks at SC. This is not a Gordon Bell kind of run. This is actually more of a science run where they're doing ice sheet modeling. And what they're doing on Stampede is actually using very high order numerics to run lots of complex multi-physics simulations and to do an inversion of Antarctica to actually infer some of the properties. So that's running on the system. The last one I have is from folks in Utah. They're running Uinta, which has been scaled up to a few 100,000 cores on other systems. And I don't have results with them from Titan yet because they're trying to get access once Titan is in production. But we have some comparisons between Stampede and Kraken, which is an older Cray at Oak Ridge. And pretty similar scaling plots. In this case, this is time, so lower is faster. As you'd expect, these are newer cores, so it's going to be faster. But pretty good scaling properties. This is up to 64,000 processors. We actually ran all of these in Stampede through the queues in production, and the scaling looks good. And with that, I'll stop and say thanks for your time. Stampede's in production now. It's got some new things that are available for the first time with some of the multicast that DK showed and the topology-aware NPI scheduling that we're working on. Scaling looked real good so far, certainly on the Sandy Bridge side. And our mic experiences are good so far, but it's a new platform, so it's going to take a while to see if there really is some good community adoption. Just the things in yellow are important things that I think you need to think about. And I'll just end with one bullet, which I think Thomas even said, which is the fact that something that is interesting, which is obvious in hindsight, but one of the things we're seeing is that people start to do their optimization work on mic, and then they go back and they compare it to Sandy Bridge. Everything that they did for mic just helped their Sandy Bridge numbers as well. So it's interesting as you start to put performance optimization into GPUs or mic, you're yielding fruit on the front end as well. So thanks a lot for your time. Appreciate it.